Hi all, thank you again for joining us this evening. I'm really pleased to present Andrew Mealor from Point Blue Conservation Science, also a graduate student at UC Berkeley. So honored to have him here with us tonight. Thanks, Drew, for joining us from Berkeley live. Drew actually I work for Point Blue as well as volunteer with the Milo Baker chapter, and Drew came to us as an intern, and so fantastic. We've kept him on, and he just continues to amaze us with all of the technology and tools that he brings to our program. And I will get into his bio. Drew is also our data guy. So for the STRAW program, he has developed amazing databases and has manage all of our tracking and data for plant and monitoring that we do. A huge amount, and also all of our volunteer numbers, et cetera. It's just a huge amount that he's doing for us. So Drew graduated with a Bachelor of Arts in Math and Biology in 2014, and he's been working with us in the STRAW program, the Students and Teachers Restoring a Watershed at Point Blue Conservation Science. And there he's helped design and implement native plant restoration projects and utilizing a climate smart restoration practices. Andrew's projects have typically been on small agricultural seasonal drainages in Sonoma and Marin counties, but lately he's been also focused on wetland transition zones where you're looking at the salt marsh to upland ecotones. He is currently a master's student in the landscape architecture department at UC Berkeley with a focus on environmental planning. And Drew, I'm going to hand it over to you. Thank you so much for joining us. And I actually invited Drew, just want to say, add one little personal piece of information. I invited Drew to talk about this tool because it is my favorite tool that we have. I feel like it incorporates all the things that you need, or that I like to see when I'm thinking about a future scenario for planting, is looking at the climate data and also soils and what are the chances of that plant making it into the future. So thanks so much, Drew.
Wow, thank you. And thank you everyone for letting me speak to you today. Just maybe to get us started, and you can raise like a real hand or use a virtual hand. Who here uses tools like maybe the Calflora website to figure out if a plant is suitable to plant at a specific location? We got one, we got a few. Yeah. Okay, so maybe it's not like a super common practice with this group, but I think it is in general within the restoration like design profession. And I think that it's worth kind of diving into the logic behind using the tools and how to use them within like a design workflow. So give me 1 second while I share my screen. So the tool that we developed for Point Blue is called cSHRMP, or Climate Smart Habitat Riparian Model Planner, which is kind of a mouthful, but it's worth it just to get that sweet shrimp acronym, because the STRAW project, which is where Leah and I work, started out as the shrimp club to protect the endangered freshwater shrimp about 30 years ago now, a while. And in this presentation, I'll start out with some like background theory methodology, kind of like a standard slideshow. And then we can pause for questions before demonstrating the actual like web tool. And if you have a question during the presentation, feel to type it in, and Lee will be keeping an eye on that. So the focus of this specific tool is on riparian restoration design in the Bay Area. And riparian restoration is very interesting because we know that riparian areas are super important for water quality and habitat quality, and so many different kinds of animals use them. But also the plants that make up these communities are very diverse. Just within the straw project, we use over 100 species in the North Bay at our planting sites. And so it's very important because we're never going to plant, as far as I know, 100 species at one project. So it's very important to figure out which plants are a good fit for a specific site. And the things that we like to think about are, of course, the project goals, which might be like water or carbon or like animal habitat. And then whether or not there's a nearby population of that species for seed flow. And if that, and similarly, if it falls within what we might consider to be like the native range of that species. And finally, we want that plant to have a good chance of survival at our project. These first three things, the project goals, the nearby population, and whether or not it's in the plant range, that's something that as a practitioner, you should probably like just know from work experience. The fourth category, the high chance of survival, is a bit harder to predict beforehand. Like we're always kind of, we're often surprised when a plant doesn't do well long-term at a site. And we can kind of break down plant survival into two main categories: short-term survival, which is going to be impacted by like the current climate, the maintenance regime, the soil, how we planted it, where we got the plant from, and the weeds on the site. And in the long term is when climate change might start to have a larger impact on plant survival. So this first category is, again, something that as restoration practitioners, we already have a lot of knowledge and experience. And the second thing, climate change, is harder for like a human to just stand at a site and try to do the math of how the different climate scenarios are going to impact all the different species. And that's where maybe we can start to bring in these tools. So Point Blue's maybe first stab at this was in 2012 to 2014 with developing a climate smart restoration checklist. And this was very helpful for leading practitioners through the thought process of climate smart design, but thinking about building resiliency under different climate scenarios. But it was very qualitative information that made it hard to visually see how all the different species are going to be impacted. And so that led to our first pass at, I think we call it like the climate smart riparian planting tool. And it was a similar thing where you input a plant, where you input a planting list, and then it tabulates how many species satisfy each of these different climate related criteria, such as tolerating wet conditions. And this had a kind of similar issues where it wasn't very site specific, and it didn't incorporate climate projections, and it doesn't tell you which of the species are filling out these different criteria. And this is a tool that I really love, the Climate Smart Watershed Analyst. And it was kind of the opposite of the first one, where it's only the site-specific factors, where you click on a location and then it tells you all the different climate projections at that spot. Super cool. And it has been taken off the internet when I was making this PowerPoint as of like 2 weeks ago. I know. But kind of an unfortunate thing about that tool anyway is that the thing that you want to do the most with it is this is Calflora from calflora.com. If you've never used that website, you are really missing out on your life because it's so much information, and it includes these pages for every species about different climate tolerances. But they calculate their climate tolerances in a very specific way. So you can't really take where it says here that Acer Negundo prefers a temperature from 20 to 59 degrees. That data isn't transferable to just any other temperature reading. Like if you have a thermometer at a site and it reaches 60 degrees Fahrenheit, that doesn't mean you can't plant this plant, because they did a lot of summarization to get to these numbers. And it was different than that watershed analyst tool, so you couldn't directly compare them. Calflora also has this tool that's somewhat newer called the planting guide, where you click on a location and then it spits out a list of plants that they think would be good to plant there. It's a great concept and it's very fast and easy to use. In my experience, it usually spits out like a huge number of species, more than you would want to plant. And some of the species, like this is for a site along Old Adobe Road in Petaluma, very exposed, heavy clay soil. I don't think we would ever plant spice bush there. So it's a little, you kind of have to take everything they say with a grain of salt, which then raises the question, when in your design process should you be using tools like this? So if you start out on the left of this image with all the species that you would ever use in the Bay Area at a riparian project, then you go out to a site. Now you're this green line, the human filter, and you only the species that make sense for that you think in your personal professional opinion makes sense to plant at a site pass through the first filter. Then you have a second filter, and this is where these kinds of tools can come in, where you pass just that subset of species through it to end up with the species that are well suited for the current conditions in your professional opinion and the future conditions in the opinion of whatever kind of tool you're using. So again, first, you're thinking about your project goals, the nearby populations, like when you're driving around, what other plants you see in the nearby area, and what plants have you seen do well at sites nearby. And then you're using some sort of like automated tool to think about long-term survival. These tools usually have a similar, there's a lot of different approaches to this, but they usually have this kind of a framework where you're taking environmental data, you're doing something with it, you're outputting a model, which is basically like a machine or like an equation. And then you're putting a climate projection through that model and it spits out a number that tells you how good of a fit that site is for that species. And for this to make sense, it needs to, like the environmental data needs to be ecologically relevant for your species and for your area, et cetera. So for cSHRMP, the data that we use comes from the California Basin characterization model, and we used 4 different climate variables: min and max temperature, precipitation, and then climatic water deficit. The temperature and precipitation are kind of self-explanatory. Climatic water deficit, if you haven't looked at that before, it's basically like conceptually the amount of water that a plant would use if it was available. So California has very high climatic water deficit in the summer because we have no water, but the plants would use more water if it was available to them. So it's very important for figuring out where different species can grow. And then we also use 2 different attributes of soil data: shrink swell, which is basically just how much clay there is, and available water supply. And we chose these variables because we thought that they maybe weren't entirely correlated with each other, like they were all unique, and because we felt like they explained the variability in where we see different species grow. So moving on to processing and model building, I'll go a bit quick through this because it's a little bit not the kind of thing that you want to talk, you want to learn about at 7:50 p.m. on a Tuesday. Basically, the data, the climate data comes in a raster format, which is like pixels of data. We overlay, and we have one map of California in the pixel data for every year from 1980 to 2009, not actually 2010. And this is based on actual observations. It's not just modeled. And then we overlay each of those years with a map of watersheds in California, and we find the average value within each watershed. Then we find the average value within each watershed across the 30 years. And then over that, we overlay plant observations and then extract the climate value to the plant observations. So we create like a data table for each plant observations has associated climate values. And this is what the tool is actually built off of. Then we create the models and we use a thing called Maxent, which stands for maximum entropy. And this is another one of those things that might not be the best thing to learn about at 7:50 p.m. on a Tuesday, but it's basically just a mathematical model that tries to find the simplest solution. So the least amount of additional assumptions, like simple, with the idea being that simple is better. And it compares your species of interest, in this case, Quercus lobata, the blue dots, against background data, which is the observations from all the other species. So it's trying to like maximize the differences between Quercus lobata versus every other species. And this approach is interesting because it gets rid of sampling bias, because we know that not only are these observations associated with climate, they're also associated with where people live, because those are the people collecting data, right? So if you compare observations from one species to another, you kind of cancel out that bias in theory. And this is what it spits out. You get a model that's like an equation, and then you can plug in the 6 values from these different environmental attributes at your location, and then it goes through the model, things happen, and it spits out a number between 0 and 1. And 1 is like highly suitable, 0 is not suitable. And it also tells you each model is created unique for each species, and the different climate variables have different levels of importance for each species. So each model, like if minimum temperature isn't important for Quercus lobata, then it just won't show up in the model. So in general, we see that the soil attributes are actually like not really important for anything. And then minimum temperature is of the climate variable seems to be less important. And the other ones seem to kind of go back and forth depending on which species you're looking at. But in general, climatic water deficit is one of the best predictors of species location. So now we can look at our different climate projections. This is in California, there's a whole bunch of different future climate scenarios that are kind of relevant. And in general, they all predict that things are going to be warmer in the future, but some say that it's going to be wetter and some say that it's going to be drier. So then like, what are we to do if we want to know how to prepare for the future? And our approach is to use these 2 models that are kind of at the extreme, like top and bottom ends of this graph, the cSHRMP, which is a warm and wet scenario, and the Mealor, which is a hot and dry scenario. So they're both warmer, but one's dry and one's wet. So that gives us 3 scenarios total. Our historic, which we talked about before, 1980 to 2009. That's what the model is built with. But then we can also plug in data from the cSHRMP, the warm and wet scenario, or the Mealor, the hot and dry scenario. And these are both looking at the period 2050 to 2079. So it works just the same, where instead of using the observed climate variables at a location, you just put in what you think the future variables are going to be, and then it spits out a future suitability score. And this is what it looks like for Quercus lobata, where in the center, we have the historic suitability, and then on the left, the warm and wet, and on the right, hot and dry. And you can see it seems to maybe do a bit better in the warm and wet scenario in the future, but overall, not as great. But these maps, which is what you often see in these kinds of studies, are like, what are you supposed to do with this? Like, it's great to see these general trends, but are you going to bring a binder full of these maps for every species out into the field with you? No. You need some sort of like decision-making framework. And for that, we use a threshold value where if the suitability score is above a certain level, then that's like a thumbs up. And if it's below it, it's a thumbs down. And the way we do that is for each species, you find the suitability scores for all the different observations, and you find the value that's where 95% of the observations are higher than that, which means we get a different threshold value for each species. A low threshold value implies that the model isn't very certain about what's going on, because that means that a lot of observations have low scores, and a high value is the opposite, where there's a lot of model agreement. So the same maps where we just use the threshold, it's a lot easier to see what's going on, where the green is where you might want to plant it, and the red is where you might not want to plant the species. And if we're using the framework that I've been talking about, you would want to plant in a location that's green in all three maps. So back to this, we've just explored this red GIS filter a bit more. And the way that this would work within an actual workflow is, first step, you make your list. Second step, you plug that list into cSHRMP, and then you evaluate if it says a species isn't a good fit any longer, how is that going to impact your project goals? Like if it says, for example, arroyo willow isn't a good fit, and arroyo willow is like the backbone of how you're going to be dealing with erosion at your site, then that's a big deal. But if it says something like, I don't know, no plant is useless, all plants have a great role at a site, but maybe like grape isn't going to do so hot, you might be able to get away with planting California blackberry, which is, another viney plant that has fruit. So not saying that grape and blackberry are the same thing, but they might accomplish similar goals. And then there might be an iterative process here. Okay, so just the last bit of this presentation, this is what the tool actually looks like. So you open it up, you have a map of the Bay Area, and then these blue outlines, these are the watersheds that I was telling you about before. So each watershed only has one climate value. It's like been averaged over the whole watershed. And that makes the tool just run faster. So you click your location, and the orange outlines here showing the soil units, which have like a different boundary than the watershed. It'll spit out the soil type that you selected and what watershed you're in. And then you can input a planting list in a couple different ways. And it will load up the Maxent model for each of those lists and then plug in the environmental variables for the location that you clicked. So this is a little bit of a mess to explain it a bit. This first dot for Quercus lobata is the suitability under the MyRock scenario. And then the second one is the historic scenario. The purple dot is the cSHRMP scenario. And then this black line is the threshold. So we see that all three of the dots are above the threshold. So the fact that they're different heights don't matter. All that matters is that they're above the black line. We also have these other 5 species where not all the dots were above the black line. And these are the ones that would make you go, and then you'd have to do some more investigating about how it's going to impact your project. So for example, the Corylus cornuta, all those dots are pretty far below the black line. And I'll say we did plant it at this project and they all died. So it's it does imply something, I guess. We also planted the Sambucus and they did great. So it's not perfect. And this whole thing is very, very much a work in project. And that's the end of this presentation. And I just want to say that as we take questions now and during the demonstration, like very open to any kind of like criticism or ideas for improvement. These are just some of the limitations to acknowledge that, yeah, it's definitely not perfect. The main ones involving sample size and our choice of climate variables. Like, for example, I would love to include fog because we know fog's very important. But did you know that there's not a great climate model for fog for like future scenarios? It's true. And some of our species, like the Quercus lobata, that are super important. This model doesn't do a great job of predicting their occurrence. So that's kind of interesting. All right, yeah, I think that's where I'll leave it if anyone has any questions now, and then we'll do a demonstration of the tool where you can like ask any questions also.
So Drew, you're looking for questions on like how you, like what you just showed us, like how you built the tool.
Yeah,
how-
like any clarifying? I see maybe Sean.
Hi, Drew. This is very fascinating. I was wondering why the different species have different black lines as for suitability. What is
Yeah,
that? Threshold, you called it. Yeah.
yeah. So Quercus lobata that we can see here, hopefully this is still big enough to see on your screen, has a pretty low threshold bar. And that happens, because there were a lot of observations when the model was being created of Quercus lobata that had a low suitability score at their observed location, which
I see.
you would assume that because they're there, they're growing there, that it's a suitable location, right? So that's not a great sign for the tool. And that can happen when the climate variables that we chose to use to create the tool are not the right variables that predict where the species grows. And just anecdotally, we're not the only one doing this kind of approach. I think there's a similar project at Pepperwood Preserve. And they also found that Quercus lobata, out of all the species they looked at, were hard to predict. So it's kind of like it's just kind of a weird thing, maybe because it can tolerate a lot of different conditions, it's very robust. Whereas heteromeles seems to be very sensitive to climate.
Yeah. Is there a possibility that people are misidentifying that
Yeah,
species and then, yeah, like mixing it with Gariana or something, which would artificially increase the range?
Yeah, not only that, but this climate data is coming from a specific range of years. I think it was 1980 to 2009. Some of the observations aren't during that time period.
Mm.
And Quercus lobata, I mean, they can live for like 600 years, right? So they could have been growing under a climate that doesn't even exist anymore. Like they could have sprouted under a climate that is very different from even the 1980 to 2009 climate.
Thank you.
Yeah, great question. Oh, okay.
I've got a question.
Oh, yeah.
Hi, nice to see you, by the way. So you mentioned sort of comparing current project survival to what was predicted here. I wonder if you've looked back at some of the older projects, like the first ones done with the in the climate smart way, because I know a lot of those died. And I wonder if this could actually have predicted that.
Yeah, so I think we haven't done like a retrospective study, which would be a really great way to validate and train these kinds of tools further. And we've talked about it. I've talked about it with some of like the interns within the straw program, because it could be a cool capstone project. And it hasn't happened yet. And that would be a great set of sites to test it on too.
Cool. Let me know if you do that.
Okay.
So I have a question. Oh, let me see. I have a question for you, Drew. You decided, can you hear me? Is that okay?
Yes.
Okay. You decided to plant the Sambuca, even though historically and low water, is that correct? Hot and low, hot and
Oh,
dry.
cSHRMP. Yeah. I think the cSHRMP is the I have to
Wet.
double check now, but the wetter one.
Okay, so but you decided to plant it even though it fell below. Why? What you've gone to this model, you're using this model, and then you override it. And I was just curious why you would do that.
That is a really great question. And that's exactly, I think, the kind of question that should be asked whenever you use a tool like this, which is that if the tool tells you something that you don't like, what are you going to do? In this case, I have a great excuse, which is that we planted this project before I made this tool, and I just went back and put it in. Yeah, but that I think that if I had made it, if I was doing it today, I might still plant the Sambucus. And what you would have to think though is, okay, if the Sambucus, if the tool's right and I'm wrong, if the Sambucus dies, what's going to happen to my project? Is there enough resiliency within the other species? And maybe you would adjust the planting numbers so that you're not totally relying. Something to also think about when letting these kinds of tools be part of your decision-making process is that when we don't really fully know how good the tool is, you want to be able, you want to implement the project in a way that you can later assess how good these tools are working across projects, which might mean you plant a handful of the species that you think would be good, but the tool says would be bad. So that if they live, then that's like that can inform about whether you want to keep using in the future. If you only do what the tool recommends, and even if it works, that doesn't tell you that the things that it's saying wouldn't work actually wouldn't have worked, because you need to have kind of both things in order to get like with testing, like a false positive or a true positive or a false negative and a true positive result. You need all four categories in order to be able to assess the validity of the model.
Thank you. Well, I can certainly see where this is valuable when you're on a large project and you don't want 60% of your
Right.
stuff to die.
Right.
Then you're willing to make some risk. I just was curious what you're thinking on that particular plant, particularly since historically it didn't rate. And if it was just, it is very valuable as a food source for the birds. So I didn't know what the project was specifically and how you came to plan it. But as you say, it was after the fact that you found out it was borderline. So thank you.
All right, if there's no further questions, maybe since I did take up a lot of time with the presentation. We'll just do it like a real quick run through. Do you think we have time for that to just see how it works? Yeah.
Yeah, I think so. Go ahead.
Okay, so this is what it looks like when you open it up. It won't really display the data correctly. Oh, and I can give out the link to this, but I haven't yet because I'm not a computer scientist and I don't know what happens if more than one person uses it at the same time. So here I go. The first step is to select a location, and let's see if I can find. I was going to try to do one of Leah's projects actually, which is near Camp Meeker, which is over here. And I think it's on this road. And then to help find your site, you want to get pretty close. There's the option to use satellite imagery. Is this where that project is about, Leah?
Yes.
Yeah. And you can also see the soil map units on here as well, which if you haven't ever explored like the USGS websites, and I think UC Davis has a version of it too. Very fun. So it's very fine scale. Each of these orange lines is a different map unit, so it'll give you a different result. Though we saw that soil wasn't even that important for most of the species. So if you click here, it'll show you your soil map unit, which you can click on that and it'll tell you more about the soil type, tell you what watershed you're in. And these watershed names are from some sort of like government program that I hardly know what they're referring to half the time. And then a land acknowledgement for the native peoples who you're in their ancestral range. Then the next thing you do is you input a species planting list, and you can either just click around on these little icons, and you can only do species which are already included in the tool, for which I think there's like 170 or something like that. But you can also copy and paste them like this. And then that populates this graph. So you can see Leah did this. They're all good. Just right off the bat, of course.
Well, I did put a lot more in there just to, I
Right.
kind of like threw a lot more in, and then I said, well, some of them didn't even have historic, so I pulled them out.
Yeah, I think one example there was Quercus lobata, which is again a weird species. So this had it very low for all three scenarios under the line. Though we saw that the low threshold value means that this Quercus lobata is kind of a weird species. Oh, I should have had, let's,
What happened?
oh, I don't already have it open. If you look at the Calflora website, and this is a great intro in case you have never looked at it, they also show that the occidental area is kind of like a dead zone for Quercus lobata. So they're picking up on the same things, which is interesting around like Healdsburg. It's a weird species. And the other thing it throws up is, I didn't talk about this in the presentation, but like relative phenology for fruits and flowers. And this is kind of like, you kind of just squint at it. The bigger the bubble, the more likely there is to be that particular type of phenology in that month. So like this one for Acer macrophyllum in March is big for flowers, small for fruits, and then later in July is when it's saying more likely to be fruits. And the idea here is that you would want there to be you want to have a large coverage of flowers and fruits over most of the year. So you don't want all of your big bubbles to line up in 1 month for either the blue or red ones, so that there's resources throughout the year. Yeah, so I can, can you run a sample model of grasses or other herbaceous species? Yeah, we can. I have to try to remember if I did Lamus or Elamus. Elamus, is that correct? Or is it Lamus?
It's now Elamus.
Okay, cool. That's good.
It's switched. You're safe either way.
Though, I don't know, it would have been embarrassing in front of CNPS. So this is showing that they're also good, which would make sense because those species are found everywhere. And that's going to be true. I mean, I'm just going to hazard a guess if I was to put up coyote brush, that it's also going to be fine. Oh, almost not in the future. So the species that are very common and grow everywhere are going to be fine mostly. Except I guess this might be too hot for peyote brush in the future. What are some other good forbs? Oh, this one. That's interesting. Oh, and actually Elamus wasn't good. Also surprising and worrying. Yeah. So if you do use this and you have feedback, I would love to know. And I think maybe my email was shared in that bio, or you can email Leah too. I just, and if you have any, and if, are there any other questions about to go over while I have this part of the tool up?
Drew, you want to scroll down to the phonology too?
Yeah.
Just curious so people could see what that might look like.
This part of it, there's a lot of missing data. This data comes from the US Phenology Network, so it's nationwide, so it's not specific to the Bay Area. That's pretty hard to find. Other websites like Calflora, they'll have a phenology graphic, but it's pretty easy to like go out and see a plant in flower when according to most of the databases, it says it should not be in flower because it's so locally dependent. So that's why I think this thing especially you should take with a grain of salt.
Could we look at the grasses and forbs again? Or you added the grasses and forbs into
Yeah.
that one. Oh, okay, gotcha.
And they didn't show up in the phenology because they must not have data on it from that data set. All right then. Thank you so much for letting me talk to you about this. I can give any relevant resources to Leah, and then you can share that out. Okay, cool.
Yeah. Thank you, Drew. Really appreciate you sharing the tool with us. And is it something that that you're willing to share a link? Are we ready to do that?
Yeah, for sure. And if
Okay.
it doesn't work, I don't know, maybe maybe try refreshing. It's a little bit strung together.
Okay.
Very nice presentation. Thank you.
All right,
Lot-
yeah.
Lot to think about.
Thanks. Thanks, Drew. And thanks
Thank
everybody
you,
for
Drew.
joining.
Thanks, Leah.
We'll see you guys next time. We have Lorenzo Washington from UC Berkeley joining us next month. And Wendy, do you know if that one's going to be in person?
No, I don't know. We need to check with Lorenzo.
Okay. So stand by. We are going to be checking with each month for our general meetings will be dependent on everyone's comfort and what the guidance are according to our local health department as to whether we'll be doing in-person gatherings for our meetings. So it's possible that next month could go in person. And if not, we always love to see your faces on Zoom too. So we'll see you again next time, hopefully. Thanks, everyone.
Great. Thank you, Leah. Bye-bye.
Bye.